Equipotential surface or line is basically a region in space where if a particle goes from one point of that to the other point, the potential is the same. So it doesn't gain any kinetic energy. So for a point charge, what does its equipotential surface look like? Okay, basically it's any 2 points where the V2 minus V1 is 0, right? So that means I have to find 2 points to integrate where the electric field dotted into the dr is going to be 0. Well, it's actually any 2 points along a sphere. Or I'm going to actually have to draw the two-dimensional counterpart of that, which is a circle. Okay? In reality, this is going to be a sphere, but I can't draw a sphere on the board, so I'll just draw a circle. So let's say this is R1, right? If I were to integrate from this R1 to this this is R2, right? But let's say R1 equals R2. So I go along the edge of the arc of a circle, or the edge of the sphere, right? What would be the potential difference between these 2 points? Well, the electric field is like that. Right? The electric field is like that. Right? And the dr is what? If I'm going that way, the dr vector is the vector that's tangential to the path that I'm taking. Right? So what's the integral of that come out? 0. The dot product of two vectors that are perpendicular is 0, right? So that means for a point charge, all points on a circle equidistant from that point charge are at the same potential. So we call that equipotential line or equipotential surface. You see? So and from here we also can generalize this. We can say equipotential surfaces are such surfaces that are always perpendicular to the electric field lines of that charge configuration, right? So if I have a dipole charge configuration, we learned in chapter 23 how to draw the electric field lines of this, right? What are going to be the equipotential surfaces or lines of this? Okay, this is going to be the electrical equivalent of a hill and a valley. The hill and the valley, the equipotential surfaces are going to be like the constant height surfaces. Circle, 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 circle. So it's going to be high over here. Then when you go to the valley, it's going to go low, right? So, and it's always going to be perpendicular to the E field line. So it's going to be like this. See, perpendicular, 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 perpendicular. Now, in the lab, we did this, right? But first, we drew the equipotential surfaces, and then we went backwards to draw the E field lines by drawing them perpendicular. So now we're doing opposite order. We first learned how to draw E field line. Then we can learn to do the equipotential by making them perpendicular. They look like ellipses, where this is one of the foci of the ellipse, right? They're not circles. Okay, this isn't at the center of the ellipse. And then there's a middle one. See, perpendicular, 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 and then there's another one. Now, if you go to my website, there's a link that I put there. It says physics simulation website. Click that. It's going to take you to a physics simulation website. And there's a simulation there that shows you equipotential surfaces. Three-dimensional version of this. It's beautiful. It's a Java program. And they show you these little hills. You could put any charge there that you want. Q minus Q, 2Q minus Q. You could do any combination, and then it'll draw the equipotential surfaces of that charge configuration. So, so let's say, for example, let's say this is 1 nanocoulomb. This is minus 1 nanocoulomb. Right, minus 1 nanocoulomb. And let's say they are 4 meters away. Okay, we could use what we just learned, right, to do the equipotential surfaces of this. If this is, let's say, 10 volts, 1 meter away, let's do like this. Let me just draw one less. Let me make it with a little less clutter. Let's say this is, you know what, let's do it this way. Let's make him 6 meters away. So let's say they're 6 meters away, and then this is equipotential surface 1 meter away, 2 meters away. The 3 meters away would be in the center, right? And then there could be 4 meters away, and then 5 meters away, and then this is at 6 meters away. So what would be the equipotential surfaces? Now, if I want to just know the relationship, I can say one of them. I can say the potential of one of them. Let's say the potential of this one is, let's say, 8 volts. Find for me the potential of the equipotential surfaces of the other one. Okay, but then in a minute, I'll show you how to actually find the equipotential surface. Okay, but now all we're doing is the relationship between them. If I tell you one of them, you should be able to get the other ones. Right? Well, we learned that as you go away from a negative charge, the equipotential surfaces get bigger, right? So from 1 to 2, it gets bigger by 4.5, right? And then when you get to this, it was 1.5, was it? 1.5, right? So that should be 14 volts. So this was an 8-volt line, 12.5-volt line, 14-volt line. This one should be, well, now I'm getting close to the 1. So now it should be another 1.5, right? See, if this didn't exist, if this positive charge didn't exist, it would keep getting, just keep getting bigger, but it would keep getting bigger less and less, right? 14, then it would get 15, then it would get 15.8. 16.1, it would get bigger by little increments. But since there's a positive charge over there, now the increment increases again, 14 to 15.5 volts. Right? And then from 15.5 to what? Another 4.5, which gives you what? 20. And then if I get closer, it's going to be even more, like